to the Blissful Mass Extreme Tartaria event.
One more. I need one more. I love one more.
Welcome to Tartaria. The Tartaria server, Discord. And the floor is yours. Today we have Bob the Science Guy showing us sextants. This should be good.
In the flat earth community. Now, this is a nautical sextant. This is a Davis Mark 25 sextant, and it's a pretty standard nautical sextant. It's accurate for navigation. So I've used this a number of times to find locations on Earth, both here at my home and all over the state of Michigan. And my accuracy is on the order of about 2.5 to 3 nautical miles, which isn't too bad for an amateur. Now, what I wanted to do today was kind of address some problems that I've seen with people talking about the sextant in the flat earth community. A lot of people seem to want to talk about the sextant, but really don't have a good idea of what the sextant actually does. So let's see if we can get a little close-up right here. And I'm going to see whether or not I can make this work. Alrighty. So we're going to bring this out a little bit, and I'm going to go ahead and share this video. I'm making a video here, a raw video for publication on my channel after some editing. But let's see if I can go ahead and get this for you. Okay, let's get rid of that background. We don't need that. Give me a second just to fix that. You know, I do these things all by myself, so sometimes it's a little difficult when you don't have a producer helping you. So
No, I feel you. I know exactly your struggles.
okie dokie, I think that should do it. Now, why is that blurred?
You have a Logitech camera or something? Yeah, it's out of focus. It was in focus for a minute, and then it went blurred.
It's in perfect focus. I see it just fine. Let me just double check it and make sure that it's right here. That a little better?
Oh, yeah.
Let me go ahead and get it so that it's here.
Yeah, and then it just went blurred again. Like it was
Make
perfect.
that a little bit smaller.
And then all of a sudden it went it's like the frame froze actually.
Really?
Yeah. It's like whatever you did like right after you're like, is that good? I was like, yep, and then it clicked again. Now it's frozen and blurry.
All right. Well, then what we're gonna do is we're gonna try and restart it. How's that?
Yeah.
Well, that's irritating. I either get to send it to Discord or I get to send it to my streaming software. So what we're going to do is I'm going to go ahead and do my laptop screen. Put that in the background. Going to get rid of that. All right, we're cooking with gas now. All right, so let's go ahead and go over the parts of the sextant. All right, now right here, you're going to see a small telescope, okay? And you look through this telescope out through this mirror right here, which is called the horizon mirror. Can you see that one there?
Yep.
Now, the interesting thing about the horizon mirror on this particular model, some of them are split down the middle, and one side is silvered and the other side is clear. This entire mirror is semi-silvered, which means it's kind of like a tinted window. And the interesting thing about that is, of course, that you can get a reflection off of it and you can see through it at the same time. I'm going to go ahead and get rid of my camera here too, because you don't need me in this. There we go. So it's a little easier for everybody to see. So you look through the telescope right here. And as you go through, you look through this mirror and you see the horizon out in the distance. So that's one mirror system that we have. Now, on the bottom, you'll see a scale that goes up to 135 degrees, and it's got a movable arm right here. It's going to be difficult for me to move it, but by pinching this, you can actually slide that arm up a little bit like so. See that? There we go. And what you do is then you read off an angle in this window, which is in whole degrees. And then down on the vernier right here, what you do is you can read off the minutes, and it goes, it goes in increments of 1 minute, which is 1 nautical mile on the surface of the earth. Now, I'm going to put that down for a second. Okay, that's good. All right. Now, I'd like to ask everybody a quick question. Okay. Oh, there's one other aspect of the sextant we need to mention, and that is right here. Now, this is the index down at the bottom, and this is called the index arm. And attached rigidly to the index arm is the index mirror. And as you move this index mirror back and forth, you change the angle on this. As you move the index arm back and forth, you change the angle on the index mirror up here. Now, I do want to ask everybody a real quick question. Let me turn this off. Now, what I want to ask everybody real quick is, what does a sextant measure? Does anybody have any idea?
What's the angle
Can
from?
people respond?
Yeah, everyone here should be able to respond and unmute. My understanding is it's the angle of something in the distance from you to it and the horizon. You're getting an accurate degree off of that.
Okay. Is it an optical measurement or a mechanical measurement?
Ooh. Let's see, because you're using a mechanical object to measure an optical event. So I don't know, it's a mechanical measurement.
Correct. It's a mechanical measurement. Let me go ahead and show you the sextant again. And I would like you to tell me what you think is going on here. All right. What is that optical measurement, or what is the mechanical measurement of? So, for example, that thing's backwards. Let me flip that around. Let me go ahead and transform this. So what are we actually measuring?
Yeah, like, boys, what's going on here?
Okay. What are we measuring? What are we actually measuring with the sextant?
For the
I've got no
I
fucking clue,
I
bro.
just joined. Could we just explain? it to
Yeah. We just kind of joined.
Okay, well then
Okay.
why don't you be quiet and listen for a few minutes,
Yeah,
and
Bob's
you'll catch
explaining.
up real quick.
We have
I
Bob the
So-
apologize.
Yeah,
It's
we have
just that
Bob
you're
the.
asking
Hold
a
on.
What we're
question.
measuring,
Go ahead.
okay, what we're measuring with the sextant itself is we're measuring the angle of this index arm to the body of the sextant. All right. Now, when we look at the sextant itself, when we look through it, all right, why don't you go ahead and go on mute if you're going to burp and hiccup and stuff, okay? Because it's kind of disruptive. Now, as we look through,
Jesus Christ! Can you please stop? I don't want to have to boot you, but that's a little bit rude. Sorry, Bob.
all
Go
right,
ahead.
if he interrupts one more time, let's go ahead and get him booted, okay? Because this is kind of serious stuff. How many people here think that you're measuring celestial objects with a sextant? Anybody?
I mean, you're measuring like the position that the object was in when the light went into it, but
All right.
like what?
So, as you look through the sextant right here, all right, you're looking at one celestial object through this horizon mirror. And it's called the horizon mirror just because that's what it's called. It doesn't necessarily mean you're measuring the horizon. For example, you could turn it on its side and you could measure two objects on the shore, or you could even have it at an angle like this and you can measure the distance between the moon and the sun, for example. So the first thing that you do is you go ahead and look through the telescope and through the horizon mirror, and you just line something up with it. Then what you do is you actually move this arm so that that top mirror moves. And say you have an object that is above you. What you're trying to do is you're trying to move this arm so that that object in this mirror overlaps the object in this mirror. So for example, if this is your horizon and this is the sun above it, what you want to do is you want to move the arms so you bring the sun down to match the horizon. Now, when you're doing this for real, there's a technique that you use where to get a more accurate measurement, because if you're looking at two objects, two round objects, for example, how do you tell they're exactly overlapping? It's very difficult to do. Generally, what you'll do is you'll bring one down until it just touches the one below it. You'll bring the top one down until it just touches the one below it. And then that's where the celestial navigation comes into play. So what you're doing is you're simply moving this top index mirror so that a reflected object above it reflects off of the horizon mirror and through the telescope, and it matches up with an object that you see through the horizon mirror. Now, let's go ahead and do some science here real quick. Dum, dum, dum. Dum, dum, dum. Dum, 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 dum. Okay, so let's go see what I have right here. I'm going to go ahead and flip this again. Okay, so here's my junior physics optical experiment box. Well worth purchasing. It's about 25 bucks on eBay. Let's go ahead and open her up. Now in here, we've got a couple of interesting devices. First, we have a laser, like so. And then we've got a couple of mirrors. Now, come on. Now, if the mirror is perfectly perpendicular to the laser light or normal to it, you see how it's reflected directly back to where the laser originates from. Now, what happens if we rotate this mirror so that it's 15 degrees? We make a change of 15 degrees, which is one of these little knobs. Okay. Notice that what happens is, even though it's only a 15-degree change with the mirror, we get a 30-degree change with the reflection. You see that?
Interesting.
Likewise, if we go 30 degrees, we're up at 60. Now, the reason for that is that as a light comes into a mirror, in other words, if the normal line here is 0, because we're going to hold it perpendicular to it, the reflection of that light equals the incident angle that it comes in. So if it comes in at 30 degrees, it comes out at 30 degrees. So that's why you get a doubling of the amount of, you get a doubling of the angle with a change in the mirror. So for every 10 degrees change in mirror, you get 20 degrees change in the angle, and that's why, because of that normal angle. Now, that's why you have that's one of the principles that you have with the sextant. This mirror, now the horizon mirror is fixed, okay? It's directly in front of the telescope and it's set at a slight angle. Come on. And it's set at a slight angle. And as you move the index arm, you change the angle of that mirror. And for every 10 degrees that you change the angle of this mirror, you change it 20 degrees from the horizon, from the baseline of 0.
Mm.
So here's a question for you. When you listen to a lot of the people in the flat earth right now, what are the things that you hear about angles? For example, what is an angle? We've often heard that it's two straight lines. Okay, where are the straight lines on the angle on the sextant? The straight line is between the body of the sextant and the index arm of the sextant. Second of all, what about this angle right here? So I've got a little compass right here, and would everybody agree that that compass forms an angle? Anybody disagree with that?
I don't think you're going to find anyone here to disagree with that point.
Great. Does that change the angle?
No, definitely not.
So all this nonsense about curved adjacents or whatever shape the angle is measured over is a bunch of nonsense, because that angle is the same as that angle. It doesn't matter.
I think part of the argument is
in any way, shape, or form.
Is that bottom leg of that angle that was touching the surface would have to be curved in, and somehow that's going to change.
Which of these angles are curved?
Yeah, so it would be the bottom limb.
Are there any curved?
Yeah.
That's not part of the angle. Okay, the angle is between the body of the sextant, which goes between the telescope and the horizon mirror, and the index arm.
Right, so it's safe to say the bottom limb that's going out to the horizon is not following the exact surface of the Earth.
Okay, now that's another question. That's another very interesting question. Does this instrument measure the path of light? Does the instrument know whether or not the light is going straight, it's being refracted, or it's being reflected.
Yeah, I don't know.
It does not.
Suppose you don't take that into account, do you?
It does not know what it's looking at. All it knows is that it sees one object here and it sees another object here. And you adjust the arms until those two objects coincide with each other. Okay? It has no idea what path the light is taking to bring those objects to your eye. You're just looking through the telescope and you're lining up two objects. That's it. Okay? So whether or not it's refracted or reflected doesn't matter. All you're doing is lining up objects, and then you are measuring the angle that you have to adjust this index arm to make those two objects line up. So the shape or the path of the light is irrelevant. The shape or the shape of the object that you're measuring it over is irrelevant. Can anybody tell me on this instrument how you measure a triangle? So there's no right triangle being measured here. You're simply measuring an angle between the body and the index arm. All right? So there's no adjacent because there's no triangle. It's simply the two legs of an angle. All right?
Mm-hmm.
This instrument does not tell you how far it is to the geographic position of a star. It doesn't tell you how far it is to the star. It doesn't tell you the angular size of the star. It doesn't tell you anything about it other than here's the star and here's the horizon, and I have to move the index arm this many degrees to make those two line up. So, any questions so far? So we've dealt with curved adjacents, irrelevant. We've dealt with refraction, irrelevant. We've dealt with dip angle, irrelevant. It has absolutely nothing to do with the angle that is measured by this instrument.
I just have two
any
questions?
questions?
Right? I just have two questions.
Of course.
Just like a genuine question, are you Bob Sextants?
What?
I'm
Bob the
just asking.
Sextants?
No, because the voice chat is named explained by Bob. It says
This event is explained by, and that's the
I see.
playlist it's in, yeah. And this is
Okay,
Bob
I
the
see.
Science Guy explaining
and
sextants.
number two, oh, okay, I get it. And number two, your name is Research.
Do you have a valid? Do you have a
Yes.
valid question?
This is a valid question. I'm
Okay.
just trying to like set the tone here.
I'm also Shamrock Bank's Observatory and Slide Rules in Mathematics.
This is true.
As a matter of fact, I'm also Otis the Tomcat Cam. So, because Otis doesn't have opposable thumbs because he's a tomcat, so he can't use YouTube,
I see.
but he shoots all the video for me.
Mm.
So, do you have an actual question related to the subject of this conversation, which is how a sextant works?
No, not necessarily.
Okay.
Okay.
Does anybody
Well,
else?
Does
'Cause-
anybody have an actual question about how sextants work?
Yeah. So I was gonna ask. Could you use a sextant for like any other measuring device other than navigation? Is this a useful tool for like
Of course.
surveying or something like that? Like if you wanted to do like a
Well-
homemade surveying system.
Well, my mom always taught me never use a crescent wrench as a hammer. Use the tool for what it's designed to be used for. Now, what a sextant does is it allows you to find the angle required to make two objects line up with each other. Now, one of the things that you can use a sextant for, obviously, is celestial navigation, and that's an entire course on what you do with celestial navigation. The other thing that you can use it for is triangulation. So say you have a lighthouse and a radio tower out on the shore. If you turn the sextant on the side and zero it in on, say, the lighthouse, and then move the index arm so that you bring the radio tower to coincide with the lighthouse, you can find the angle for triangulation between those two and locate your position. If you know the distance between those two objects and the angle, you can kind of figure out what your distance from what your distance from shore would be, for example. The other thing that I'm going to be using it for is I'm going to go out in the backyard and I'm going to measure the distance to the sun with this. And the way that I'm going to do that is after the method of Aristarchus. Now, Aristarchus reasoned that at the first and the third quarter of the moon, where the moon was precisely 50% lit, if you measured the angle between the moon and the sun at that moment, you could create a right triangle with the distance from the Earth to the moon as one leg, the distance from the moon to the sun as the second leg, and the hypotenuse would be the distance from the Earth to the sun. Now, the current measurement is that is 89 degrees, 53 minutes, or 89.85 degrees. And that corresponds to a distance to the sun of 392 times the distance from the Earth to the moon. Now, my goal is to go ahead and measure that myself in the backyard when the first or the third quarter of the moon is up during the daytime and I can see the moon and the sun at the same time. I'll measure the angle between the two using a sextant. And then I will use that to calculate the distance from the Earth to the sun in terms of the distance from the Earth to the moon. So that's another thing that you can use a sextant for.
Interesting. Now, how are you going to
And
look
obviously,
at the... how do you angle in the sun without, like, burning your eye out? Are you going to...
Great question.
Oh, cool.
You put your sunshades down. That's why they're there.
Didn't know they had them.
All right.
Very cool.
Yep, there's 3 of them. So what you do is there's 3 of them on each mirror. And what you end up doing is putting down, and you put them all down at first. And if you have a little trouble making out the sun, you can take one of them off at a time to see if the sun, is bright enough for you to be able to see it. You don't use those for stars for celestial navigation. Now, there are 58 navigation stars and some planets. Okay, these are bright stars. And they're all over the Earth, okay? You don't have to see them all at the same time. You know more or less where you are. You know what stars are going to be in your sky. So you're not going to be looking for stars that are in the southern hemisphere, for example. And what you do is you measure them just before dawn or just after sunset during twilight. So you have enough light to be able to see where the horizon is, and the star is bright enough that you can see it. And what you do is adjust that index mirror until you bring the star down to the horizon. And then you read off the angle from the sextant itself. Then from there, you go into all the calculations of celestial navigation. Now, if anybody's interested in looking at celestial navigation, I've got a great video of me actually taking a noon sight and doing all the math involved with it on my channel. And I'm going to go ahead and see whether or not I can get that for you. So give me a second. Let me switch over to this.
No, those solar filters, those are a specific type of shade.
Hang on just a second. Come on. All right. So let me see if I can find that for you.
He's got to beat level 9 in Tetris. Hold on, guys. He's playing it on the side.
Yeah, I got to beat level 9 in Tetris. And here's the sextant taking a noon sight. Now, one thing that I really want to emphasize for you guys, you can see this here real quick. Let me go ahead and flip it around so you can see it. Let's make that big first of all. All right, so this is all the math that's involved in this. But see which one that is. Now, Here's something that's kind of interesting. You see, I am pointing the sextant down. Does anybody know what I'm doing? And I'm doing a noon sight here. Does anybody know what I'm doing or why I'm doing it?
Oh, are we supposed to be seeing a video right now? I don't see one.
No, you should be seeing an image. Do you see an image?
No, I see you
No,
still.
we do not see.
Oh, give me half a second. Let's go see if we can fix that. My apologies. Okay, I think I've got this.
Sorry, but is your name research?
All right. Do you see that now?
There we go.
I'm sharing it live. Okay. Now notice what I'm doing with the sextant is I'm actually pointing it down. Does anybody know what I'm doing?
Are you establishing an angle to your local horizon?
I'm actually using what's called an artificial horizon. So on the ground, I have a bowl of water. And what I am doing right now, why is this not? Here we go. There we go. So what I'm doing here is I'm looking down into a bowl of water at the reflection of the sun. And the reason that I'm doing that is that obviously I live in a town. I don't have a clear view to the horizon. So let's go ahead and see what I'm doing. And this goes to show that the sextant literally does not know what it's looking at. So
Lie?
let's go look at this.
Alright.
What?
All right. So right here, so we've got the ground. And what I've got is I've got a little bowl of water right here. And the top of the water is level to the surface of the ground, or flat if you want to call it. Now, if you look up here at the sun, what I'm doing is the sun is coming down and reflecting off this little pool, and it's coming back up at the same angle. So you see this angle right here is the same as that angle. Now, I'm looking down at the sextant with a telescope. Okay. Now the index mirror is angled such that it's looking up at the sun. Now remember, these are parallel right here. These are two parallel lines. Now, this angle right here, if you were to divide this in half, is horizontal. Now, when you're using an artificial horizon like this, you don't need to adjust for a dip correction. You're measuring this whole angle right here with the sextant. You cut that angle in half, and that is the angle from your horizontal up to the sun. Now again, remember, I've got two suns here simply because these are parallel right here. They're
They
both
aren't to
looking at the
scale.
same sun.
Yeah.
And these
they're
are
not to
parallel
scale.
lines. Yeah, it's not to scale. And remember, this is also freehand, and it's a little awkward for me to draw it like this. So you see the angle that I'm measuring is actually twice the angle from the horizon up to twice the angle from the horizontal up to the celestial object, the altitude of the object. I'm measuring this entire angle right here because I'm using a reflection to measure it. And recall from our work with the laser, here's the normal line. So as the sunlight comes in here, it reflects out at the same angle that way. Everybody clear on that?
Yep.
It's an interesting concept. And it's very useful.
What ways would you use that in? Like
Well, Lewis and Clark actually carried a bowl of mercury with them when they were out doing the survey of the Louisiana Purchase, because they didn't really have a reliable sea horizon.
Doing?
what? Can you guys stop interrupting, please? I'm sure he's gonna open up
I'm
to
sorry.
questions soon.
Just this guy is like ripping a blinker on camera. Like, bro, what are you doing, man?
Yeah, you're interrupting right now. Please don't. Continue, Bob.
Okay. So they're out on the prairie. They didn't have a reliable sea horizon that they could go to, because they've got an undulating prairie out there. So how are you going to find your latitude and longitude? Well, they had an accurate clock with them, and they used a bowl of mercury to do a noon sight and get their latitude and longitude. And then they were also, it's a little more difficult to do it with a star, of course. Another way that you could get around that is using something called a bubble sextant. Now, a bubble sextant is a little bit different than a marine sextant or a nautical sextant. A bubble sextant measures the angle from vertical out to your celestial object. And the way that it does that is that it's got a tube with some fluid in it and a dome top, and there's a little bubble in that. And then you also have a mirror system, an index mirror system. And what you do is you adjust that so the star appears in the middle of the bubble. And that measures the angle between that little index mirror on the bubble sextant and the vertical line as defined by where the bubble is in gravity. All right. So that you don't use a dip correction with that or anything like that. You don't need a horizon. And altitude, of course, doesn't matter with either of the sextants, other than the fact you have to put a dip correction in some cases with a marine sextant where you're measuring from the horizon, which is below your horizontal.
Very cool.
Now the dip correction. Now I really don't want to get into celestial navigation here. I think that the main thing that I really wanted to emphasize in this presentation was how a sextant actually works and what it actually measures. So the next time you hear somebody go on about triangles or a curved adjacent, or angles have to have straight lines, it's all nonsense. The angle does have a straight line. It's, the index arm of the sextant to the body of the sextant. Okay. It doesn't care what surface it's over. It doesn't care if it's refracted or reflected, nor does it know whether or not it's refracted or reflected. All it sees is an object in the telescope, and you move the index mirror so that you line those two objects up. And once you do that, you measure off the angle that you have to set the index mirror to make that happen. And from there, you take it and do your celestial navigation. So,
and how much
sextant does not measure size, it doesn't measure distance, and it doesn't measure the line of sight or anything like that. Certainly doesn't measure triangles.
So what's the tolerance for something like that? Like because you're gonna have diffraction or refraction through the atmosphere. What's the tolerance for a sextant?
My accuracy, and I'm an amateur. All right. I'm formally trained in navigation, but all my stuff is GPS and VORs and things like that. But my accuracy with a sextant is about 2.5 nautical miles.
Okay.
So the proof's in the pudding. Now, the minimum distance on a sextant, if you're an expert at it, you may be able to get it within a nautical mile or even a little bit less. Remember, 1 arc second, which is 1/36 hundredths of a degree, is 109 feet on the Earth. 1 minute of angle is 1 nautical mile, 6,080 feet, give or take. All right. That's the definition of what a nautical mile is. It's 1 minute of angle. And 1 degree of angle, of course, is 60 nautical miles.
So pretty accurate.
The idea with a sextant, it's pretty accurate, yes. The idea with a sextant is not to not to survey in, the corner of your property. The idea with a sextant is to get you close enough to the mouth of the port that you can see it and sail the rest of the way in under something called pilotage, which means direct vision. You go between the markers and you go right in the channel, right up, right into the port. But you should be close enough with a sextant to be able to see the port.
Very cool. Yeah, it was very informative. Like I had a rough understanding of what you generally did with the sextant, but it's definitely a lot more involved with it.
And what it does not do, it doesn't measure the adjacent. It doesn't measure the surface underneath you. It lines up two objects and tells you what angle the mirrors have to be held in order to do that. Then you go from there with the mathematics of celestial navigation. Now, when you look up at an object, you're going to see the object in the mirror, okay? And you're going to line it up with another object, okay? Once you have that angle, you have to take into account standard refraction, for example. Now, a lot of people think standard refraction is a big deal. It really isn't, all right? When you're looking at an object in the sky, once you get your measurement, you do a correction for standard refraction. And that correction, if it's 90 degrees from your zenith down to 45 degrees, your error at the zenith is 0 because you're at the normal line. As you come down to 45 degrees, your error is 1 arc minute. So if you don't correct it at all and your object is over 45 degrees above the horizon, the most you're going to be off is a nautical mile. The rest of it's on you, man. The rest of your error is on you. But you can correct for that nautical mile by subtracting 1 arc minute from your altitude. Now, when you cut that in half and go down to 22.5 degrees, you're at 2.25 arc minutes. So you see, it really doesn't change that much, and it's well known what that change is. And that change is verified by 2 ways. 1, it gives you an accurate position, and 2, you can compare it against, say, a bubble sextant, which measures from the zenith down, and you can get a very good, you get a lot of information from that. And 3, you can measure the lapse rate of the atmosphere, which is what controls refraction. And 4, you can measure the refraction directly. And the way they do that is they take 2 lasers, a red laser and a blue laser. They're parallel to each other, and they shine it out over a distance. And then they measure how much of a change that each of those 2 lasers have. And because they're different frequencies, they bend and refract at a different rate. By finding out what refraction you have on those 2, you can find the base refraction of the atmosphere directly. So these are things that we measure all the time. This is the entire purpose of putting up weather balloons, is to measure the atmospheric lapse rate. So now, when the other side of this equation is something called the dip correction, and that is the angle from your horizontal down to the horizon. Now there are three factors in the dip correction. One is your height above the surface. You have to factor that in. The second thing that you have to factor in is the refraction down by the horizon, which can get rather significant, up to 0.5 degree. But those things are known. And the third thing, of course, is the curvature of the Earth. And if you put the numbers, okay, say we all know that for a 6-foot person, the horizon is approximately 3 miles distant. Okay, so we know our horizon is 3 miles away. Simply by comparing the flat Earth to the spherical Earth, we can calculate what that dip angle should be, and they're quite different. Okay, the dip angle on a spherical Earth is much steeper than on a flat Earth. And you can compare that against reality.
You know,
and you can compare it against the
you're
nautical.
honestly very wrong.
Hold on.
And how so?
Yeah, go ahead and ask a question. then.
Because you're not getting faded than a whole bitch. Bro, you really think the earth's flat?
I'm sorry, but we're not gonna be calling names and shit like that. You can
Bro,
come
what the
back
fuck
on,
was
but
that?
yeah.
Demons,
Demons.
Does anyone have a real
That
question
was a
for
full-on
Bob?
fucking demon. What was that guy doing?
All right. So
Wait.
if you incorporate those three factors, the height above the surface, the curvature of the earth, and the refraction, you will get the dip correction that's listed in the Nautical Almanac. Using that dip correction, you will find your look in a little bit of skill with the sextant. You'll find your location within 3 to 5 nautical miles. That's the proof that those are correct. So we have, if you want to play the scientific method thing, our hypothesis is that the Earth is a sphere and the atmosphere refracts this amount. We measure the refraction. We take our readings. We use the refraction to adjust those readings, and we come up with our position. Is our position accurate? Because we can accurately determine our position by other than optical means. So, for example, there are survey positions, there are GPS positions. We can compare our calculated position to our GPS position, and you'll find that it's very close. I think the most error I ever had, was 14 miles. And the nautical sextant is using an artificial horizon is a little bit more accurate than the bubble sextant is, simply because of operator error. You're trying to estimate where the star is in the center of a moving bubble. That takes a little bit of skill to do, but I still got pretty good readings with it. I got within about 7 nautical miles with the bubble sextant.
Yeah, I've never heard of a bubble sextant. That sounds like an interesting tool. I'm gonna have to look more into that.
Yeah, you want to see one?
Yeah, definitely.
Yeah, let me show you one. Oh. This is a World War II Link Mark 12 bubble sextant. It's the same sextant that my stepdad carried on his plane. Down here, you've got battery and light source, which is in the case right now. And right in here, where'd we go? Okay. So right here, you have an eyepiece. And inside here, you have some glass, and you also have a shade like you have on the other ones.
Mm-hmm.
And what you do is you just look down through here, and in the casing down here, there's a small vial that has xylene in it. And that xylene it's like an inverted test tube or an inverted blood draw tube. So it's domed on the top.
Right.
And there's a small air bubble in it. So what you do is you adjust the index mirror here with this dial, and that makes the index mirror move back and forth. And then it's kind of like a reflex gun sight. You just look through it and line up the star with the center of that bubble. And that's the way, and what it does is it measures the altitude of the star from the vertical.
Cool.
But that's a Link sextant. Now, the other thing is the sextant. Yeah, where'd I put that thing? Oh, there it is.
It's hiding
All
behind a huge telescope.
Why is it called a sextant? Not up here, it isn't.
I always,
It's
as a
hiding
child,
behind my auto level.
as a child, I always wondered why they called it a sextant, and I had many wild ideas.
Okay. So you see, this says 120 degrees right here. Now, as you recall, this is the measured angle of 120 degrees to the altitude of the star. Now, because of the reflection, this is actually only 60 degrees. Okay? 60 degrees is 1/6 of a circle, hence a sextant. If it was 90 degrees, it would be a quadrant. And this one is 45 degrees, and it's an octant. So it's called a bubble sextant commonly, but in reality, this is an octant. So you see the difference in the size of the index arc.
Right.
This one's much shorter than that one is. This is 45 degrees total. That's 60 degrees total. That's an octant. That's a sextant. Here's the original case for this
Oh, nice. I love
Link
cases.
A12, and it just smells old. Yeah, it just smells old. There's a couple of rather interesting things I've managed to pick up on. Yeah, something's wrong here. I don't have that on backwards. There we go.
Does anybody have any questions for Bob about using a sextant or anything like that? Oh, sorry. Kid named Finger, you're unmuted now.
I don't see why I was muted in the first place.
We're being disruptive. Do you have a question, though?
No.
All right, no problem. I thought the presentation was informative. I learned a lot. Oh my God, don't break anything.
Shit.
It was expensive.
No, I'm looking for something in here that I can't find. You know, one of the things that I like is I like slide rules. You know, a lot of people don't even know what these things are anymore, but they're what calculate orbits. You know, the original orbits were calculated with slide rules. But I actually have a slide rule from World War II that was used to calculate charges for 105 and 155 millimeter howitzers. And, you know, you put in the distance and it'd tell you how many bags of powder you had to put in.
Nice.
So it was a cool little thing. It was kind of standard issue. And then, of course, you know, we've got the whiz wheels.
Yeah, I had a mechanical calculator when I was a kid. It was my dad's. Should see if I can find
You talking
that.
about the type that had the lever on the side? Or
It was a handheld one. It was tiny. It was like something you.
But
put
some of
on a
these
notebook.
things, you know, there's another concept in science that I think that a lot of people, you know, characteristic number 5 of science denial is an inappropriate expectation of perfection from science. And there's a concept of close enough is good enough in science. So how much error you're willing to tolerate depends on how much error you need to have an accurate answer. So, for example, with slide rules, you're only good to about 3 significant digits. Now, I have one slide rule that's good to 5 significant digits. But most of your calculations in engineering and things like that, that's close enough that you can get a working answer with it. You don't need to have it out. You know, you don't need to calculate pi to 100 digits. The difference between pi to 100 digits and pi to 5 digits is not that much. So it's good to be able to do the exact number every now and then, you know, or get very, very close. But generally, a quick and dirty calculation will get you into orbit. Then you fix it from there if you have to. You know, it'll be a small fix. So, anybody have any questions? Okay. Well, thank you all very much for your attention. I hope it was. I hope you found it interesting.
Yeah.
And you know a little bit more about the Davis Mark 25 sextant.
Yeah, I definitely think it was very informative.
Purchased for me by the patrons of the channel, patrons and members of the channel, as was the auto level and as was a lot of the telescope gear.
Awesome. I'm going to put your links in the bottom of the video here. I'd like to thank you for coming and doing another presentation. This has been explained by Bob the Science Guy, explaining sextants. Thanks for stopping by, man.
All right. And by the way, anybody that, you know, in the flat earth that pretends to tell you how a sextant works, ask them one simple question. One, have they ever used one? I have. And I've demonstrated that I can use them properly. So until Nathan Oakley or QE, who still thinks that, there's triangles involved, or 10th Man, or Brian's Logic, or whoever these guys are, they don't have the first clue as to what a sextant measures, much less what to do with that measurement. I've just explained to you how these things work. Now, the next step is to learn a little bit more about celestial navigation, and there's a few videos on my channel that may be able to help you with that. So in the meantime, thank you very much. I'll stick around for a few minutes in case anybody comes up with any questions afterwards. But I think we're pretty well set here. So let me go ahead and shut this down. You're very welcome.